Picture this. You're 250 miles above Earth, floating inside the International Space Station. Your crewmate stops responding. Their body goes limp. They're gone. What happens next? The answer is more complicated and disturbing than you think. Right now, as you're watching this video, there are people living 250 miles above your head on the International Space Station. They're traveling at 17,500 miles per hour, orbiting Earth every 90 minutes. And here's something most people never think about. NASA has no official protocol for handling someone who has passed away in space. That's not a joke. Despite decades of spaceflight and hundreds of astronauts launched into orbit, there's no written procedure in NASA's official handbooks for what to do when someone passes away up there. The Flight Director's Handbook lists dozens of emergency scenarios, but it's treated like a taboo subject that nobody wants to acknowledge. Passing away in space isn't just possible, it's inevitable as we push further into the cosmos. And the challenges of dealing with a deceased astronaut are unlike anything we face on Earth. Since the beginning of human spaceflight in 1961, only 18 people have passed away during spaceflight operations. 3 of those occurred above the Kármán line, the boundary of space at 62 miles altitude. Those 3 were Soviet cosmonauts aboard Soyuz 11 in 1971. The others were during launch or re-entry, like the Challenger disaster in 1986 and Columbia in 2003. But here's the critical difference. All of those tragedies involved total mission failures. Everyone passed away at once. We've never faced the scenario of one astronaut passing away while the rest of the crew survives. That's the situation we're completely unprepared for. Let's start with the most likely scenario. A spacewalk gone wrong. Every time an astronaut steps outside their spacecraft, they're one small puncture away from disaster. Space debris travels at speeds up to 17,500 miles per hour. A paint chip the size of a grain of sand can punch through a spacesuit like a bullet. There are over 100 million pieces of space debris orbiting Earth right now. Most are smaller than a marble, but they're all deadly. A fleck of paint traveling at orbital velocity carries the kinetic energy of a bowling ball dropped from a skyscraper. Your spacesuit, despite being incredibly advanced, can't stop that. If your suit gets punctured during a spacewalk, you won't explode like in the movies. But what actually happens is almost worse. The air rushes out of your lungs instantly. Your blood doesn't boil, but the moisture on your tongue and in your eyes starts to vaporize. You'd have about 15 seconds of useful consciousness before you black out. In 1965, a NASA technician accidentally depressurized his suit in a vacuum chamber during testing. He remained conscious for 14 seconds. He later reported that he could feel the saliva boiling on his tongue before everything went dark. He survived because they repressurized the chamber in time. In space, there's no emergency repressurization. You'd lose consciousness in 15 seconds and die within 2 minutes. Medical emergencies are another real threat. Astronauts are in peak physical condition before launch, but space does terrible things to the human body. Bone density decreases by 1 to 2% per month. The heart weakens because it doesn't have to pump against gravity. Blood pressure changes. Radiation exposure increases cancer risk. A heart attack, stroke, or sudden medical crisis could happen at any moment. The International Space Station orbits within Earth's magnetic field, which provides some radiation protection. But astronauts still receive about 150 millisieverts of radiation during a 6-month mission. That's equivalent to about 1,500 chest X-rays. On a Mars mission, without Earth's magnetic field protection, astronauts would receive 300 millisieverts during the journey alone. Then there's the psychological factor. Imagine being trapped in a space the size of a 6-bedroom house with the same 5 people for 6 months. No privacy. No escape. No ability to step outside for fresh air. The isolation and confinement have driven people to the edge before. While NASA screens extensively for mental health issues, the stress of space is unlike anything on Earth. So an astronaut has passed away. Now what? The first challenge is immediate and practical. You're stuck in a sealed environment with a body. The International Space Station is about the size of a 6-bedroom house, with a total pressurized volume of 32,333 cubic feet. There's nowhere to go. No way to step outside for fresh air. You're sealed in with your deceased crewmate. The body starts decomposing immediately. Within minutes, bacteria in the gut begin breaking down tissue. The human body contains trillions of bacteria, and when the immune system stops functioning, they multiply unchecked. Within hours, the smell becomes overwhelming, and you can't just open a window. The station's air recycling system would spread that smell throughout every module. Every breath you take would remind you of what happened. Temperature control becomes critical. The human body is about 60% water. In the station's normal temperature of 70 degrees Fahrenheit, decomposition accelerates rapidly. Bacteria multiply at optimal rates. Gases build up inside the body, causing it to swell. This isn't just disturbing. It's a genuine health hazard for the surviving crew. The gases produced during decomposition include methane, hydrogen sulfide, and cadaverine. These aren't just unpleasant. They're toxic in high concentrations. The station's air scrubbers are designed to handle carbon dioxide from breathing and trace contaminants from equipment. They're not designed to handle decomposition gases from a human body. The International Space Station has no morgue. There's no cold storage designed for human remains. Every cubic foot of space is precious and planned for specific purposes. So, where do you put a deceased astronaut? The most practical option is the crew quarters. Each astronaut has a sleeping pod about the size of a phone booth, roughly 6 feet long by 3 feet wide. It's private, it can be sealed off, and it's one of the few spaces that could be spared. You'd have to secure the body inside, seal the compartment, and lower the temperature as much as possible. But here's the problem. The station's cooling systems aren't designed to freeze a 180-pound human body. The temperature control system maintains comfortable living conditions, not morgue conditions. The best you could do is keep it cool, not frozen. Decomposition would slow down, but it wouldn't stop. Some experts have suggested using a spacesuit as a temporary body bag. Seal the deceased astronaut in their suit, vent the air to create a vacuum, and let the cold of space do the work. Without oxygen, bacterial decomposition slows dramatically. The suit would be exposed to the vacuum of space through the airlock, where temperatures drop to -250 degrees Fahrenheit. But spacesuits are expensive, critical equipment. Each suit costs about $12 million and takes years to build. Using one as a body bag means losing a backup suit that could save a living astronaut's life during an emergency. It's a difficult trade-off with no good answer. Now comes the really difficult part: getting the body back to Earth. The Crew Dragon capsule that brings astronauts home from the ISS is tiny. It's designed for living passengers who can sit upright in form-fitting seats. The interior is only 13 feet in diameter. A rigid, deceased body doesn't fit that design. You can't just strap a body into a seat. Rigor mortis sets in within 2 to 6 hours after death, causing the muscles to stiffen. The body becomes rigid and difficult to position. And remember, you're in zero gravity. Moving a 180-pound rigid object in a confined space without gravity is incredibly difficult and dangerous. One wrong move and you could damage critical equipment or injure the living crew. The capsule's life support system is another issue. It's calibrated for living passengers who consume oxygen and produce carbon dioxide at predictable rates. A decomposing body releases different gases: methane, hydrogen sulfide, cadaverine, and putrescine. These gases could overwhelm the air scrubbers or create toxic conditions for the living crew during the journey home. The re-entry process creates its own problems. During re-entry, the capsule experiences forces up to 4 Gs. That means everything inside weighs 4 times its normal weight. A 180-pound body suddenly weighs 720 pounds of force pressing against whatever it's secured to. If it's not properly secured, it becomes a deadly projectile that could kill the surviving crew members or damage the capsule systems. In 2005, a Swedish company called Promessa proposed a solution called the body back. It's designed specifically for space deaths. Here's how it would work. You place the deceased astronaut in a special sleeping bag made of durable material. A robotic arm extends the bag outside the spacecraft into the vacuum of space through the airlock. The extreme cold of space, around -250 degrees Fahrenheit, freeze dries the body within 24 to 48 hours. All the water sublimates directly from ice to vapor without passing through a liquid phase, leaving behind a freeze-dried corpse that weighs about 50 pounds instead of 180. The water vapor disperses harmlessly into space. Then comes the disturbing part. The robotic arm vibrates the bag at specific frequencies. The frozen, brittle body shatters into small fragments, like breaking a frozen flower. What was once a human being becomes a fine powder that can be stored in a small container about the size of a large backpack, roughly 20 inches by 15 inches. It sounds horrific, but it's practical. The remains take up minimal space and weigh only 50 pounds. There's no smell, no decomposition, no health hazard to the surviving crew. The family receives the remains in a form that can be buried or scattered according to their wishes. NASA has consulted with Promessa about this technology, but the system has never been built or tested in actual space conditions. The cost and ethical considerations have prevented its development. Everything we've discussed assumes you're near Earth with a quick way home. The ISS orbits just 250 miles up. A Crew Dragon can return to Earth in about 24 hours if needed. But what about Mars? A Mars mission takes 6 to 9 months each way, covering a distance of 140 million miles. If someone dies on the journey to Mars, you're stuck with the body for months or even years. You can't turn around. The orbital mechanics don't work that way. Earth and Mars align for efficient travel only once every 26 months. The launch window lasts only a few weeks. If someone dies during the outbound journey, the mission continues. The crew has to live with that reality every single day for the rest of the mission. Storage becomes critical. A Mars spacecraft would need dedicated cold storage for human remains. Some designs include a small compartment that can be depressurized and exposed to space, essentially creating a freezer using the cold vacuum outside. This compartment would need to be at least 7 feet long and 3 feet wide to accommodate a human body. But here's the ethical question nobody wants to answer. Do you bring the body back to Earth, or do you leave it on Mars? Bringing it back means dedicating precious cargo space and fuel to transporting remains for potentially 3 years. Every pound of cargo requires fuel to accelerate, decelerate, and maneuver. A 180-pound body could mean sacrificing critical supplies or scientific equipment. Leaving it on Mars means the first human buried on another planet won't be a pioneer who chose that fate. They'll be someone who died unexpectedly, possibly tragically. Their grave would be 140 million miles from their family. There would be no way to visit, no way to pay respects except through photographs and video feeds. Some astronauts have already made their choice. They want to be buried in space if they die there. It's seen as the ultimate honor, becoming part of the cosmos they dedicated their lives to exploring. Several astronauts have stated publicly that they'd prefer space burial to returning to Earth. A burial in space from the ISS would be relatively simple from a technical standpoint. Place the body in a spacesuit or special container. Depressurize the airlock and release it during a spacewalk. The body would initially orbit Earth alongside the station at 17,500 miles per hour. But orbital mechanics are unforgiving. Without propulsion, the body would gradually lose altitude due to atmospheric drag from the thin upper atmosphere. The ISS itself has to be boosted regularly to maintain its orbit, rising about 1.2 miles per month to compensate for drag. A body without propulsion would descend faster. Over weeks or months, depending on the initial altitude, the body would descend lower and lower until it hit the denser atmosphere about 50 miles above Earth. Then it would burn up like a meteor, vaporizing completely at temperatures exceeding 3,000 degrees Fahrenheit. The entire process would take about 30 seconds, leaving nothing behind but dispersed atoms. Some people find that poetic. A final return to stardust. Others find it disturbing, an undignified end for a hero. Either way, it's a practical solution that eliminates the storage and transport problems. But it requires advance permission from the astronaut and their family. You can't make that decision for someone else. And international law would likely require consent. Here's something most people never consider. Who has jurisdiction over a death in space? If an American astronaut dies on the International Space Station, is it an American death? What if they die in the Russian segment? What if a Russian astronaut dies in the American segment? What if a European astronaut dies in the Japanese module? International space law is murky on this point. The Outer Space Treaty of 1967 says that nations retain jurisdiction over their own spacecraft and crew members. But the ISS is a collaborative project with modules from the United States, Russia, Europe, Japan, and Canada all connected together. The station operates under a complex framework agreement signed by 15 nations. Death investigations require autopsies, evidence collection, and legal procedures. None of that is possible in space with the current facilities. The body has to return to Earth for proper examination. But by then, decomposition and the conditions of space travel have destroyed most forensic evidence. Tissue samples degrade, toxicology becomes unreliable, physical evidence is contaminated. If foul play is suspected, proving it becomes nearly impossible. The confined environment, the stress, the isolation, these are perfect conditions for conflicts to escalate. History shows that isolated groups under stress can turn violent. But investigating a potential crime scene 250 miles above Earth with contaminated evidence and no way to secure the scene is a nightmare scenario that keeps lawyers awake at night. So, what does NASA actually do when asked about death in space? They deflect. Official statements say things like, NASA does not prepare contingency plans for all remote risks. It's the same superstitious logic as not talking about a no-hitter during a baseball game. Acknowledging the possibility feels like inviting disaster. But behind closed doors, NASA has thought about this extensively. Astronauts receive training on how to handle medical emergencies, including death. They know the basics. Preserve the body as best you can. Document everything with photographs and detailed notes, and get home as quickly as possible. They practice these scenarios in simulations, though the emotional reality would be far different. The International Space Station has a small medical facility with basic life support equipment. If an astronaut's heart stops, the crew can attempt CPR and use an automated external defibrillator. But CPR in zero gravity is incredibly difficult. You can't compress the chest effectively without something to brace against. Special techniques have been developed, but they're far less effective than on Earth. If those efforts fail after 30 minutes of attempts, there's nothing else to do. You can't call 911 from space. You can't rush to a hospital. The nearest emergency room is 250 miles straight down. And getting there takes at least 24 hours even in the best circumstances. Communication with mission control becomes critical. The flight director would immediately coordinate with medical experts, legal advisors, and the astronaut's family. Every decision would be documented in real time. Every action would be recorded on video. The surviving crew would receive psychological support from Earth, though talking to a counselor via satellite with communication delays isn't the same as in-person therapy. As we push deeper into space, death will become more common. It's simple statistics. Longer missions mean more exposure to radiation, more time for medical emergencies, more opportunities for accidents. Mars missions could last 3 years round trip. Lunar bases might become permanent settlements with hundreds of people. Space stations could house thousands. We need real solutions, not just theoretical discussions and deflections. That means designing spacecraft with proper morgue facilities from the beginning. It means developing reliable methods for preserving or disposing of remains that respect both the deceased and the living crew. It means training crews not just for the technical challenges, but for the psychological trauma of losing a crewmate far from home. Some companies are already working on this. SpaceX, Blue Origin, and other private space companies are developing their own protocols. They know that commercial space travel will eventually result in deaths. Being prepared isn't morbid. It's responsible. It's acknowledging reality and planning accordingly. The first person to die in deep space will be remembered forever. They'll be a tragic footnote in history, but also a reminder of the risks we accept when we explore the unknown. Their death will force us to confront questions we've been avoiding for decades, and hopefully it will push us to develop better solutions for the astronauts who come after them. Death in space isn't a question of if, but when. As we venture further from Earth, we'll face this reality. The solutions are complex, disturbing, and necessary. Because exploring space means accepting every consequence, even the darkest ones.